Good afternoon. Welcome to today's Carnegie Science Zoom program with global ecologist Anna Michalak. Our program will begin in just a few minutes. Please be patient as we allow attendees to sign into the webinar. And remember, you can submit your questions at any time using the Q&A button on the Zoom platform. Good afternoon. Welcome to today's Carnegie Science Zoom program with Carnegie global ecologist Anna Michalak. Our program will begin in just a few minutes. Please be patient as we allow attendees to sign into the webinar. And remember, you can submit your questions at any time using the Q&A button on the Zoom platform. Thank you for your patience as we allowed participants to sign into the webinar. As a reminder, you may submit questions at any time using the Q&A button on the webinar platform. We will now begin our program with an introduction from Carnegie President Eric Isaacs.
I'd like to start by talking about this moment in our nation's history as we have seen a nationwide response to the killings of George Floyd, Breonna Taylor, and Ahmaud Arbery. Over these past few weeks, all of us have been called upon to examine and bear witness to the impacts of racism on our nation and on our lives. These impacts, of course, extend to the world of science. And as a world-renowned research organization, the Carnegie Institution for Science has a duty to take a leadership role in addressing these issues within our own organization and throughout the American scientific community. We ask for your support and we welcome your ideas on how we can open the doors of science more widely to people in every community. And now I have the honor of introducing my distinguished colleague, Anna Michalak. She currently serves as the director of Carnegie's Department of Global Ecology, and she joined us at Carnegie in 2011 from the Department of Civil and Environmental Engineering at the University of Michigan, where she was the Frankenbrook TransU faculty scholar. Anna holds a bachelor's degree in environmental engineering from the University of Guelph in Canada, and she earned her MS and PhD in civil and environmental engineering at Stanford University. She did her postdoctoral work at the National Oceanographic and Atmospheric Administration's Earth System Research Laboratory. As you'll hear, Anna's research centers on the ways in which human activities affect the environment and drives climate change. Her work includes global studies of the ways in which climate change threatens water quality. And as you'll hear, Anna also is a leader in the study of greenhouse gas emissions at scales ranging from single city to those that embrace the entire planet. Last year, Anna led an effort that used atmospheric models and satellite data to reveal that China has not been fulfilling its commitment to reduce methane emissions from coal mining. Today, she is going to talk with us about the ways scientists unravel the complex systems that contribute to our climate and about how scientific models can be used to set real, effective goals for reducing emissions and to create strategies in order to meet those goals. Her research is fascinating and urgently important. And like you, I'm really eager to hear what she has to say today. So please join me in welcoming Anna Michalak.
Thank you, Eric, for the great introduction. And thank you, Natasha, for hosting the seminar. I'm going to start by sharing my screen. Great, and now you should be able to see my slide as well as a pointer that I'll use. And so as Eric mentioned, my lab works in two different areas related to climate change. And the one that I decided to talk with you about today is some of the ways that scientists track the interactions between the global carbon cycle and climate impacts, so that we can understand how human impacts are changing the climate system today, and also how we will alter the climate system going forward. And this lovely animation that you see here is from colleagues at NASA, and I'll tell you a little bit more about it later on, but hopefully you've been enjoying looking at it while we were waiting for the program to start. And so to begin, I wanted to start with something that we all know, which is that temperatures have been rising roughly for the last 150 years. What you see on this graph is a year on the horizontal axis going roughly from 1850 to today. And on the vertical axis, you see temperature change in degrees Celsius. So multiply roughly by 1.8 to, if you tend to think in degrees Fahrenheit. And what you see in the yellow line is the human-induced contribution to the roughly 1 degree Celsius of temperature increase that we have seen so far since the pre-industrial era. And so when we talk about limiting climate change to, let's say, 1.5 degrees centigrade or 2 degrees centigrade, keep in mind that we've already crossed the threshold of 1 degree centigrade as of a few years ago. But we also know that climate change, while temperatures are of course very, very important, climate change involves a broader range of impacts beyond just temperatures at the global and regional scales. And to give you a summary of that, I took this figure from another report from the IPCC, which is the Intergovernmental Panel on Climate Change. And this is from their 5th assessment report published in 2014. And what this pictogram shows you is, for North America, the types of systems for which scientists have been able to quantitatively attribute changes in certain systems to changes in climate. And so if I focus for a minute on this mid-latitude region in the United States, all of these symbols that you see that are filled means that climate change has had a major contribution to changes that we've observed in certain systems. So for example, the blue water droplet here means that climate change roughly in these US mid-latitude has had a major contribution on rivers, lakes, floods, and droughts. And the symbol on the right-hand side in red says that climate change has already had a major contribution to people's livelihoods, health, and the economy. And so all I want you to see here is that there's a very large number of filled symbols, and the same would be true if you looked at other regions around the world. And so climate change is impacting not just temperatures, but a variety of ecosystems, but also human systems that we use to sustain ourselves and our communities. And so where are we today? So today we have the Paris Agreement, which is the current international agreement that governs how countries are tackling the challenge of climate change. And if I can summarize it in roughly 4 bullet points, the goal is to keep global temperatures, quote unquote, well below a 2 degrees centigrade temperature rise above pre-industrial conditions, and to actually endeavor to limit the temperature rise to about 1.5 degrees Celsius. And the way to do this is by limiting the amount of greenhouse gases emitted by human activity to the same levels that trees, soils, and oceans can absorb naturally, roughly by the middle or the end of the century. There's an aspect of each country reporting its contributions every 5 years so that we can track how they're meeting the challenge that's before us. And finally, that richer countries will help poor countries by providing climate finance to adapt to climate change and switch to renewable energy. For today, though, I want to focus on this second bullet point because it's actually very interesting and very scientific if you look at it carefully. Because what it says is that the amount that we emit as people needs to be balanced by the amount that trees and soils and oceans can absorb. And so what this means is that we need to be able to anticipate not just how much we will be emitting, but we also need to be able to anticipate how much will trees and soils and oceans be able to absorb, not just today, but going into the future. And so this is the concept that I really want to spend a few minutes telling you about today, and then of course, diving into deeper discussions once we get to the Q&A session. So just to start, give you a glimpse at this question, what I thought I would start with is just a one picture view of where is all the carbon on our planet. And so if we go back to roughly the year 1870, what you see in these numbers here are the number of petagrams. So petagrams is the same as gigatons, is the same as billions of tons. So these numbers represent the number of billions of tons of CO2 or carbon that were embedded in the atmosphere, plants and soils, oceans, and deep geologic carbon back in 1870. And when we're talking geologic carbon, we're talking about fossil fuels that have been buried for millions of years. And so this is 150 years ago. So what has happened since? 2 things have happened since. The first is what we started to do as human beings is, first of all, dig up carbon that had been stored for millions of years and burning it, thereby injecting it into the atmosphere. And the second thing that we've done is to engage in quite a bit of land use change. So we've converted forests into agricultural lands and so on and so forth, thereby putting some of the carbon that had been stored in plants and soils into the atmosphere as well. So this is what we have done. At the same time, what has happened is that plants and soils and the global oceans have naturally responded by actually pulling carbon back out of the atmosphere at a pretty impressive rate. And so again, it's hard to think in units of billions of tons, But if you just look roughly at the amount of total CO2 that we have put into the atmosphere, approximately half of that has actually been pulled back out of the atmosphere by plants and soils and oceans. And so another way of thinking about this is that climate change would be happening twice as quickly if it weren't for this free service that the terrestrial biosphere and the oceans are providing to us. And this is this idea of balance that the Paris Agreement is referring to, right? And so we want the numbers here on the left to roughly balance numbers here on the right come a few decades from now. And so the question is, how do we get there? And how we get there involves understanding what is it that's making plants and soils and oceans take up all this additional carbon from the atmosphere. And so next, what I want to do is give you a bit of a shorter term snapshot of what these different components look like. And these are now figures from a program called the Global Carbon Project, which assesses the state of the carbon cycle on a global scale year in, year out. And so now you're looking from 1960 to today, the amount of gigatons of CO2, and gigatons turns out to be the same as petagrams, just different people use different names for the same unit. So year in, year out, this is how much carbon we're emitting from fossil fuels, how much carbon we're emitting from additional land use change. And so we can see, of course, that fossil fuel emissions continue to rise. And then year in, year out, this is our best estimate of how much of that carbon is ending up in plants and soils on land, and how much of that carbon is ending up in oceans. And finally, of course, the remainder ends up in the atmosphere. And so what you'll see is that all of these years are above zero, which means that every single year we end up with more CO2 in the atmosphere than the previous year. But the amount varies quite a bit from year to year. And looking at these other plots, what you can see is that most of that variability comes from variability on land. Going back to the atmosphere, though, it turns out that on very large scales, measuring CO2 in the atmosphere is actually relatively straightforward compared to measuring carbon on very large scales on land and in the ocean. And so what I want to do is show you a little video that has many, many components. So you can choose where you want to focus your eye. But before I start the video, I'll just show you what you will see where. And so in this big panel, what you're looking at is going from the South Pole all the way to the North Pole. What are concentrations of CO2 in the atmosphere, which you see on the vertical axis? In this little map, you see in a particular year, where did we have measurements of CO2 available in the atmosphere from around the world? So you'll see the number of observations increasing. And then what you'll see in this area, as I start the video, will be overall how are CO2 concentrations on a globally averaged level changing over time. So let me start the video and I'll show you a few more things. So the first thing you might see in this red line is this constant going up and going down. And what that's representing is this seasonal cycle of CO2 in the atmosphere. And so during the Northern Hemisphere summer, plants take up a lot of carbon. And then during the Northern Hemisphere winter, they release a lot of carbon. And because most of the land mass is in the Northern Hemisphere, it turns out that on a global level, primarily what we see is the impact of this Northern Hemisphere biospheric response. The second thing you see, of course, is that CO2 concentrations are going up year in, year out. You already knew that from the previous slide. What you see on the left is this sort of interesting wave that, again, you can see is in response to the biosphere in the Northern Hemisphere turning on and turning off between the summer and the winter. But then this nonstop rise in CO2 that's due to the net emissions from fossil fuel burning and cement production and land use that's driving CO2 concentrations higher and higher over time. The other thing you'll notice is that as we get to dates that are closer to today, you can see that we have many, many more atmospheric observations than we had a couple of decades ago. And I'll come back to that in just a minute. I'll pause the video just for 1 second. The last thing I'll point out is that you'll see that in more recent days, we have a lot more noisy observations. And that's because while we used to have observations only in faraway regions from major urban centers, we are now more and more measuring CO2 in areas that are more directly impacted by local human activity as well. As I restart this video, it'll go back further back in time to before we had direct atmospheric measurements of CO2, but where we have proxy measurements from things like ice cores that show us how CO2 concentrations have varied on much longer timescales. So now you can see this part of the video going back to the 1970s into the 1950s, where the very first atmospheric record was started at Mauna Loa in Hawaii. And then going even further back in time, you're looking at now pre-industrial times, and as the animation continues, you'll even see how CO2 concentrations have varied over various ice ages and even further back in time. And so you can really begin to see how the kinds of concentrations we're seeing now, which are now over 400 parts per million, are truly unprecedented on even geologic timescales. So now we're up to looking at about 300,000 years BCE, and now about 1 million years BCE. And you can just see how today's concentrations are dramatically different. So I've shown you 800,000 years. Let's now take a deeper dive and just look at 1 year. And so this is now no longer direct observations of CO2. What you're seeing in this video is a model simulation of what we think atmospheric CO2 looked like just for 1 year, in this particular case for the year 2006, around the world. And so you can think of this as the sort of high resolution version of the image I showed you on the previous slide. In this case, though, we don't have as many observations. So this is a model that's driven by some of the observations that we actually do have. And so it's a little bit hard to see. So everything that's red is high concentrations of CO2 in the atmosphere. And so you'll see the CO2 wafting around with wind and weather patterns, so that CO2 emitted in North America ends up in Europe and then comes all the way back around again. If you look a little bit more carefully, you can actually see the outlines of the continents. And if you look very carefully, you can even see the pulsing from day to night as we're looking here at the US West Coast, as emissions rise and fall during the day, both because of human use of fossil fuels and because of the pulsing of the biosphere, with carbon being taken up during the day and being released at night. As we switch now from winter to spring to summer, you'll notice that the colors become cooler in the northern hemisphere and warmer in the southern hemisphere, because now it's summertime. And so the biosphere in the northern hemisphere is taking up more carbon than we are emitting, but the opposite becomes true again in the winter. So you see this sort of seasonal cycle in the natural components of the carbon cycle, but then you can still see the pulsing of, I live in the San Francisco Bay Area. So for example, here in California, this pulsing of emissions of CO2 from human activity. Okay, so this is what we think the atmosphere looks like. But again, this is from a particular model of emissions coupled with a model of atmospheric transport. And so really the question that is key to achieving this goal that was laid out in the Paris Agreement is to get at this balance between the human emissions and the natural sinks of carbon. And it turns out that if you use a number of different models to analyze why is it that the biosphere is taking up all of this additional carbon from the air, it turns out that the models disagree. And so what you see in these colored bars are sink, sort of uptake of carbon that's due to the fact that atmospheric CO2 concentrations are rising, thereby providing more food for plants. Carbon uptake due to the fact that we're injecting more nitrogen, which is a fertilizer, into the system. Carbon uptake or carbon release that's due to land cover change. And carbon uptake or carbon release that's due to the climate itself changing, so largely temperatures and rainfall changing. And all I want you to see here is that the size of these various colored bars vary dramatically between all of these models. So the models tend to agree that the biosphere has taken up all this carbon, but they completely disagree in many cases as to which of these different processes has been the primary driver of this uptake. And so why does it matter? I mean, if the biosphere is taking up carbon, then wonderful. Why, isn't that end goal all that matters? Well, it turns out that if you take these different models that are fundamentally driven differently by these different components of the system, then if you look at their estimates of land uptake, roughly until today, they generally agree. But if you try to use them to project how this land uptake will change in the future, in this case going out to 2100, all of these models diverge really dramatically because they all had different opinions as to why land has been taking up carbon thus far, and therefore they have different responses to the way that climate and CO2 and land use and nitrogen fertilizer use will be changing in the future. And I'm talking primarily about land, but there's similar disagreements as to how the ocean will respond to future climate change as well. So these are all simulations from models that couple the carbon cycle to the climate system to try to anticipate how much carbon can we expect land and oceans to take back out of the atmosphere out to 2100. And so again, these are units of gigatons of carbon. I know these are not intuitive units for most people, but if you translate this uncertainty into units of parts per million of CO2 in the atmosphere, you see that this uncertainty as to how land and oceans will respond to future climate change translates to an uncertainty of 300 parts per million in atmospheric concentrations of CO2 in the year 2100. And if you think back to some of the previous slides I showed, that range is roughly the total amount, or more than the total amount of CO2 increase that we've seen so far since pre-industrial time, right? So our uncertainty is roughly double all of the climate change we've seen so far. And so what we really need to do is to understand why and how these natural components of the carbon cycle are responding today so that we can better anticipate how they will respond in the future. And it turns out that now is a perfect time to be asking these questions because, as I showed you near the beginning of this talk, there's been a huge expansion in the number of places around the world where we're measuring atmospheric CO2 in flasks, on tall towers, using aircraft, but also increasingly using other methods like these instruments that look up at the sun and are essentially a ground-based remote sensing instrument that derives how much CO2 is in the atmosphere above this instrument by looking at the spectrum of sunlight that comes through to the instrument. And even we're having an increasing number of satellites that were designed and launched specifically to measure CO2 and methane from space. So a lot of the work that my lab does, just to give you a bit of a glimpse, is develop approaches to use this wealth of newly available atmospheric measurements to figure out exactly how is the biosphere responding to climate change. And we do this by developing a set of tools that are called inverse methods or inverse problems, where we relate measurements of CO2 in the atmosphere via a model of how atmospheric transport works back to what the fluxes must have been. And so whereas in reality, the fluxes of carbon at the surface are causing the concentrations in the atmosphere, we try to go backwards. So we go from the atmospheric concentrations all the way back to what the fluxes must have been. And the problem is that there's all of these errors and all these uncertainties, and they all vary in space and in time. And so the devil's in the details, as it always is, but conceptually it's quite straightforward. And I like to think of it a little bit like a creamy cup of coffee. And so if you think of the cup of coffee as being the atmosphere of the planet, and if you think of the cream as being the atmospheric CO2, what we are doing as humans is, of course, putting all of this extra cream into the cup of coffee. And as you saw in that video, the longer the cream is in a cup of coffee, the creamier the cup of coffee becomes. And what we try to do is to essentially reverse this process, right? And so we measure the concentration of cream in different parts of the cup of coffee. And we try to, in a modeling, statistical, mathematical way, unmix the cream to figure out where the cream was poured in and when was it poured in, and maybe even more importantly, what caused the cream to be poured into the particular part of the cup where it ultimately arrived. And what I wanted to do is just to show you, one little result from one study that we published to show you the kinds of insights that this is aimed to achieve. This is from a paper from a former PhD student who graduated a couple of years ago, where what we were interested in understanding is what biomes within North America are actually contributing most strongly to this interannual variability in how much carbon North America can actually take back out of the atmosphere. And so what you see here, color-coded, are the different biomes in North America. And each dot here represents roughly the percent area coverage of that biome for North America. And what we did is to take a large number of models from an intercomparison study called MISTIMIP, which is actually led by a former postdoc of mine. And what we did in the first step is to analyze all of these models, to ask these models, where do the models think most of the variability is coming from? And these bar charts were the answer from the modeled perspective. And what I want you to see here is that there's a huge amount of disagreement as to how much of the interannual variability can be attributed to croplands versus needle-leaf forests versus deciduous forests, shrublands, and grasslands. And so what we did in the next step instead is we said, well, in more recent years, we have this wealth of new atmospheric measurements. And so we can actually pinpoint from a data-driven perspective, where is all the variability coming from? And this is what you're seeing in these new lines here with the diamond symbols. And if we just focus on the diamond symbols, it becomes very clear where that interannual variability is actually coming from. And we see that most of the year-to-year change in how much carbon plants in North America can take up is really due to changes in the behavior of deciduous forests and mixed forests. And so everything that is in this light blue color, if you look at the map here. But perhaps more interestingly for the topic we're talking about today, what we also did is we said, well, why is it that there's this disagreement in the models here on the left-hand side in how they attribute carbon uptake? And what we found, if we again zoom into these forest regions, if you look at the response of the carbon uptake in these models to changes in temperature, what you see is each of these models in a different colored line. And what you see is they all respond completely differently to variability in temperature in this particular biome. So the models disagree on how carbon uptake responds to variability in climate. But because we now have this wealth of atmospheric observations, what you see in this dotted black line is we now have an observationally driven constraint on what the correct answer is from the perspective of what we can actually measure. And so these atmospheric CO2 observations are now helping us to differentiate among models, and in this way actually informing what is the actual biospheric response, both to historical and then also to future climate change. This is then providing feedback that is directly usable not just by scientists, but by policymakers, if we think back to the Paris Agreement. And we're doing similar things also in the boreal region. You may know that the boreal region is one of the most vulnerable regions to climate change. And this is a study that's currently being done by a current PhD student, Nina Randazzo, where she's showing that the tundra and the boreal forest respond very, very differently to temperatures in the autumn, in this particular case in October. And so what you'll see is as temperatures get warmer in the autumn, the tundra ecosystem emits more and more carbon. It is very, very vulnerable to temperature change. But the boreal forests respond differently because it turns out that as temperatures warm, you not only get more carbon release from soils, but you can also extend the growing season. So you can actually have additional carbon uptake as well. So there's very big contrast in between these two biomes. Okay, so to wrap things up, as you can see, by better understanding what is driving the current behavior of the carbon cycle, we can help to narrow the uncertainty on what future carbon uptake will be, thereby allowing us to quantitatively aim at this balance between our emissions and what the natural components of the carbon cycle can actually handle. And last but not least, I did want to end with, it's of course up to us as human beings to ultimately provide the solution to this challenge. And so I wanted to go back again to the IPCC, so the Intergovernmental Panel on Climate Change, which released a report focusing on this target of 1.5 degrees centigrade total temperature rise. And as part of that report, it created a number of scenarios of ways in which we can cap total temperature increase to 1.5 degrees centigrade. And they all involved a different balance between emissions from fossil fuel industry. Here in brown, agriculture, forestry, and other land use. And then here in yellow, bioenergy with carbon capture and storage. And so, for example, one could achieve a total temperature rise of 1.5 degrees through very quick and dramatic technological innovations. Or we can achieve it by having a focus on sustainability, by shifting towards sustainable and healthy consumption patterns. Or we can achieve it by fundamentally changing the way in which energy and products are produced. But these are essentially the three big levers that we have that we need to engage as quickly as possible on a very, very large scale. The last scenario on this page is essentially a sort of a business as usual scenario where in the short term, we have continued growth of emissions, and only in the longer term do we have ultimately reductions in emissions. But the difference in the scenario where we wait longer to act is that we actually overshoot this target of 1.5 degrees centigrade and only begin to approach it at the end of the century. So I will stop there and move on to questions. And I also have a couple of comments if folks in the audience are interested in the impact of the current coronavirus pandemic on carbon emissions. I'm also happy to talk about that, even though it's somewhat peripheral to the main topic that I've talked about. And so with that, I'll pass things back to Natasha, who can let me know what questions I should start with.
Thank you so much, Anna, for a fascinating talk that really made some things so clear that are very complicated and made them very easy to follow. So much appreciated. We have a lot of questions. To start with, we have one from Marvin, who wants to know how the scientific community can be confident in both emission numbers and natural recapturing numbers when you're looking back all the way to the 1800s. How do you know that that data is good?
So let me actually go back. So the short answer is, needless to say, the further back in time we go, the more we have to rely on proxies of certain types of numbers. So let me go back to this slide and share it again. So let me answer the question at a very high level. In terms of human emissions from fossil fuel use, we feel that we have a very good handle on those because countries keep track of their own production numbers and their own consumption numbers. So I would say that those are very well known. Similarly, if we look at the amount of carbon that's remaining in the atmosphere, as I mentioned, we have this greatly expanding atmospheric network, which really allows us to track how much carbon is in the atmosphere very, very well. And land use, I would say, is quite easy to view using satellites and historical records. And so that's reasonably well known as well. And so really the most difficult part is the part that I've talked about today, which is this overall land sink. And quite often the land sink is simply estimated by doing the sort of the differencing between all the other components. So if you measure how much is in the atmosphere and you subtract back out how much carbon has ended up elsewhere, then by definition, the remainder must have gone into land. And if all you want is that one number, that's probably quite accurate. But again, what we really want is we want to anticipate what this number will be decades from now. And that's where we have to actually understand what processes drove the number that we ended up with. So I think that answered the question at a high level, but I'm also happy to go into more detail, whether now or over email later on.
Thank you so much. We have two similar questions. Phil asks, what are the negative impacts of an over-reliance on land and ocean sinks? And then Janelle similarly asks, does all of this excess carbon being taken up by the land and ocean harm them, cause them harm?
Great. So yes, there is no free lunch, no matter what your area is. So, in the oceans, depending on where the carbon is, most of you have probably heard about the problem of ocean acidification. And so when carbon dissolves into water, the water becomes more acidic. And so while we don't have necessarily direct control over the uptake of carbon by the oceans, it certainly can cause damage depending on where that carbon ends up as well. On land, it partially sort of depends on your perspective. There are areas where you have what's called woody encroachment, so places that used to be tundra that now have shrubs or might even have trees. Whether that's good or bad maybe depends on your perspective. I think perhaps the other comment that I'll make about that is that as you may have, well, here actually let me go back down to the slide. As you may remember from this slide, at least a portion of the reason for which land has taken up as much carbon as it has is because of this process attributable to nitrogen deposition. So both because we are using more fertilizer and also because we are burning greenhouse gas, because greenhouse gases, including nitrogen containing greenhouse gases, are ending up in the atmosphere, that nitrogen ends up back on land and therefore is fueling additional growth. Whether that's a positive or negative in and of itself, I suppose is arguable, but it is itself attributable to changes that we have made in the system through the process of using fossil fuels for driving our energy needs.
Thank you. And we have another pair of similar questions. An anonymous attendee wants to know if replacing mature trees with young ones could affect carbon sink. And then similarly, Miranda wants to know if planting evergreen trees or trees that are on a different seasonal cycle could affect that seasonal variation between the northern and southern hemisphere that you showed in that slide. And would that make a difference?
Great, so great questions. So to answer the first question first, I think there's really two questions that are embedded in that question. So one is, mature forests versus young forests. And this is actually a very interesting point of debate in the scientific community, where it used to be the case that the predominant understanding was that forests take up a lot of carbon, and as the trees mature, it plateaus out so that older forests are no longer taking up a large amount of carbon. And so therefore that sort of they didn't contribute quite as much as new forests. There is now a lot of debate about this. There's some data that shows that these old growth forests are actually continuing to take up quite a bit of carbon. Now, there's also the issue of, well, if you were to replace the old growth forest with newer forest, where do you put that wood? Because of course, if you burn that wood, then it ends up back in the atmosphere. There's some folks who are pushing very hard for actually using that wood in ways that would prevent that carbon from ending up in the atmosphere. So for example, using wood as a building material in long-term structures more than we do currently, which would mean that that carbon would stay sequestered and we would have additional growth from new trees. So that's certainly something that can be explored as well. But the short answer is that I would say the sort of general thinking was that forests that are at the peak of their growth take up the most carbon, but that's now being debated to some extent. In terms of the second question, even evergreen trees in the wintertime don't take up as much carbon as they do in the summertime. And while you do see this very strong seasonal cycle that I showed, I won't dig up the video again, that you saw in two of the videos that I showed, the seasonal cycle in and of itself is not a problem per se. It's just a symptom of the fact that most of the land mass is in the northern hemisphere, and therefore when the northern hemisphere happens to have summer, you have a more dramatic carbon uptake than in the southern hemisphere. But on time scales of, on the order of 6 months, all of the atmosphere ends up getting mixed around the entire planet. And what's really driving climate change, at least for first order, is just a wholesale increase of CO2 in the atmosphere on a global scale, and much less so sort of gradients between individual regions that might have slightly different concentrations of CO2.
Thank you. And we have a question from Lynn, who wonders if wetlands and estuaries have been broken out, and if they fall into ocean or land, or how do they fit into this calculus?
That is an excellent question. So they fit into this calculus in two ways. So one is everything that I talked about today had to do with CO2, so carbon dioxide, but especially regions like wetlands are very important when we think about the natural versus human components of the methane cycle. And so if you think about human greenhouse gas emissions overall, the biggest impact that we're having as a species is from our emissions of CO2, but second in line is the impact we're having through emissions of methane. And so those types of systems are very important when we try to differentiate the natural and human components of the methane cycle. But also, and also a hot burning topic of the research community is what we call lateral fluxes, right? So you can imagine there might be carbon that actually begins over land, ends up in rivers, in estuaries, in wetlands, and then ultimately may or may not make it out to the coast, or may end up being cycled as it goes to the coast. And historically, those lateral fluxes were not accounted for in a particularly sophisticated way in some of the models that I've been talking about today. But there's an increasing understanding that, number one, that flux may be larger than we thought and therefore very important in its own right. But number two, if we ignore it, then whatever that flux is, we're erroneously attributing to a different part of the system, which then further gets in the way of getting to this mechanistic understanding that I was arguing is really important for being able to project what's going to happen into the future. So I think that's a great question, and she's welcome to come work in my lab and figure out the answer.
All right, what an invitation. So we have two questions about technology solutions, and Stephen just asks generally which kind of technological innovations would make the greatest impact on fighting climate change, and then David asks specifically about carbon capture at the site of fossil fuel plants and your opinion on the effectiveness of them.
So let me reshare this screen. And Natasha, to be honest, I was attempting to find the slide while you were speaking. So if I don't answer the question fully, just ask me again. So, in terms of technological innovation, there's, I guess I'll say two things, right? So one is, there are technological innovations that would allow us to use less energy for the things that we do already. And so, if you think of LED light bulbs, that's a great example that we all have access to, that just use, much less energy than older types of light bulbs. So there's many technologies in that category. But second, there's also certain types of energy that going forward are going to be much easier to convert to sustainable sources. So for example, it's much easier to replace electricity with carbon-free sources than it is to replace jet fuel with carbon-free sources. And so there's also, if we allow approaches that make use of electricity for a larger fraction of our energy demand, that allows us to actually leverage technologies that we already have, whether it's solar or wind or other green energy sources, to fuel a larger fraction of the energy that we were going to be using. And then the second question, I think, was about carbon capture. Can you tell me, Natasha, what the specific question about carbon capture was?
Yes, David was interested in carbon capture at the site of an energy plant and the effectiveness of that.
Right. So, currently carbon capture technologies tend to be quite energy intensive themselves and quite expensive. And so these are definitely areas where future technological innovation will be incredibly important. Currently, they're primarily being looked at for sort of industrial processes that really yield very high concentrations of CO2, such as, for example, cement production. So those seem to be sort of the low-hanging fruit where that type of technology will most quickly make the most sense. But I think it's important to recognize that a lot of those technologies, at least at the current pace of technological innovation, will take some time to really have a dramatic impact. And so, if I leave you with no other messages, that as with most problems, we need this sort of all of the above solution. And so I'm a big proponent of thinking at every scale, from the individual to the international agreement. And so I think there's a large role to be played in terms of things like sustainability and reductions in demand, in addition to technological innovations, and of course changing the way in which energy is produced, so relying more on carbon-free energy sources. Because otherwise, what's going to happen is at least we will overshoot our goal before coming back down to this 1.5 degree of climate change, or worst case scenario, we would never get to the 1.5 degrees. But since we're on the slide, maybe I'll just mention one thing is in the other half of what my lab does, we actually look at what might be some unintended consequences on water sustainability of the ways in which we mitigate climate change. And so if you look at this P3 scenario here in this middle, that relies very strongly, for example, on the use of biofuels for energy. It turns out that those kinds of scenarios can have negative impacts on water quality and on things like dead zones and harmful algal blooms. And so, as with most things, you need to look at the whole system comprehensively, so that by solving one aspect of the problem, we're not inadvertently creating another problem. But I do want to emphasize that there is a lot of room for win-win solutions. And I really think it has to do with finding the right balance among these three types of strategies so that we can make the most impact in the shortest possible amount of time.
Thank you so much. We have time for one last question. There are many questions that we unfortunately did not have time to get to today, but anyone who would like to email their unanswered question to events@carnegiescience.edu, we will make sure those get shared with Anna and that you get answers. So our last question comes from Mark, who has attended all of the programs in our series, and he is very interested to know how you started this career path you're on and what made you decide to pursue this area of research.
Oh, wow. Well, that's a great last question to end on. So, I will say this jokingly, but it is true. I wanted to be a veterinarian when I was a child. and then I went to university and realized that involved a lot of memorization, and that was not something I was interested in. I'd rather figure things out than memorize things. And so I decided to become an engineer. And I've always been very motivated by finding solutions to problems that are truly pressing on, again, scales that range from the individual to the entire globe. And when I was doing my PhD, I was working on problems related to contamination of groundwater. But interestingly enough, the problems I was working on was, if you have limited measurements of water quality in groundwater and you find contaminants, how do you figure out where they came from, and therefore who's responsible, and therefore who should clean it up? And if you think back to my slides, that's very similar inverse problem to the one that I was talking about in the atmosphere. And as I was finishing my PhD, I thought that was a very important problem. I was interested in thinking at things on larger scales. And so I essentially contacted folks at NOAA, which is where Eric mentioned that I did my postdoc. And I said, hey, I've been developing these tools as part of my PhD. I think they would be useful for tracking greenhouse gases in the atmosphere. And then I was fortunate enough to win a postdoctoral fellowship that allowed me to go to NOAA and start playing around with these tools. And it's ended up being an incredibly rewarding experience all along. And I find that often, and I'm sure if Mark is a student or otherwise, but often when you sort of play at the interface between different fields, you find really exciting opportunities that someone who had been grounded exclusively in one field or another would not have necessarily found. And if I can just make a plug for Carnegie while I have the podium, I think this is also the beauty of being a scientist at Carnegie, in that we have these scientists who work in very different areas, but because we rub shoulders on a frequent basis, we end up being inspired by science in different sub areas, and that then helps to inform the work that we do. And that's what drew me here in the first place. And of course, the funniest part is that now, as I just mentioned, we're going back now to studying water again. And so as with the water cycle and the carbon cycle, you always end up coming back to where you started. But yes, so that's a short version of how I got to be here. And it's been an incredibly fun ride, and I look forward to seeing what comes next.
Thank you so much. We will now hear concluding remarks from our president, Eric Isaacs.
Well, Anna, thanks so much for a really interesting presentation, and also for the very important work that you're doing. I also wanted to thank all of you in the audience today for your interest in Carnegie Science, the work we're doing here, and for your continued support. We're hoping that you'll join us again on June 24th at 4 o'clock. It's a slightly different format where we'll be joined by the Kavli Foundation and hosting a virtual, what we call Capital Science Evening program. We're going to have a really interesting speaker, Jim Hudspeth from Rockefeller University, who'll be talking about the highly specialized sensor receptors in our ears. He calls it the biological hearing aid. And he'll share some of his work in conversation with, or interviewed by, an Emmy Award-winning journalist, Frank Sesno. So I'm really hoping that you'll join us at that time. In July, our next virtual conversation like this one will be about the Giant Magellan Telescope, which is now under construction at our Las Campanas Observatory in Chile. When it's built, it'll be the world's largest telescope. These are 24 meters of glass, and we'll be able to discover remarkable things, and we're looking forward to that talk. And as always, we very much appreciate your interest in Carnegie Science and look forward to welcoming you back soon. Thanks again.